The researchers in the room did not celebrate. That is the detail nobody talks about. When the pattern appeared on the screen, when the system pointed at a structure buried inside the prime numbers that no human mathematician had ever identified in 2,000 years of trying, the people who built that system and understood what they were looking at went quiet. Then they started questioning it. Then they started trying to break it, because what the machine had found was not supposed to be there. Not in the sense that it was impossible, in the sense that generations of the most gifted mathematical minds in human history had stared at exactly this data and walked away empty-handed, and a machine that had never read a single textbook, never attended a seminar, never absorbed a single intuition about where to look or where not to bother, had found it in the one place everyone had stopped looking. That is the story. But to understand why it matters so deeply, you have to start at the beginning. Not at Google DeepMind, not in any laboratory. You have to start with the numbers themselves and with the strangeness that has been sitting inside them since before any civilization thought to write mathematics down. Pick any number, any whole number greater than 1. Now ask yourself a simple question about it. Can it be divided evenly by any smaller number, or does it stand alone? The number 8 divides evenly. You can split it into 2 4s, 4 2s, 8 1s. It is built from smaller pieces, but the number 7 cannot be split. Nothing smaller goes into it cleanly except 1 in itself. 7 stands alone. That is a prime number. Simple enough. A child can understand the definition. Every whole number greater than 1 is either made from smaller numbers, like 8, or it resists that construction and stands completely by itself, like 7. The ones that stand alone are the primes, and they are the reason mathematics has had a persistent headache for roughly 2 millennia. Here is the first thing about primes that should bother you. They never run out. There's no largest one. No matter how far you push up the number line, into the millions, the billions, the trillions numbers with more digits than you could write in a lifetime, there is always another prime somewhere ahead of you, waiting. This was proven more than 2,000 years ago with an argument elegant enough to still be taught to students today. The primes are infinite. That much, at least, is settled. But that is the last thing about primes that is clearly settled. Because the question that has shadowed mathematics for all of those 2,000 years is not whether primes exist or how many of them there are. It is this: why do they appear where they do? Stare at the beginning of the prime sequence and you might think you notice something. 2, 3, 5, 7, 11, 13. They come quickly at first, packed close together, but then the spacing starts to behave strangely. Sometimes 2 primes sit right next to each other, separated by a gap of just 2. Then suddenly the gap widens to 4, to 6, to a long, empty desert with no primes at all, and then 2 arrive almost on top of each other again. They scatter across the number line with no rhythm anyone has ever been able to write down. You cannot predict the next prime by looking at the current one. You can only test numbers one by one and see what you find. This should not be possible. Not in mathematics. Mathematics is the one place in all of human knowledge where everything is supposed to have a reason, a chain of logic connecting every result back to something already proven. There are no accidents in mathematics. There is no randomness that lives in the mathematics itself, rather than in our ignorance of it. And yet the primes behave like confetti thrown into the air and left to land wherever they please. They are not random. Mathematicians are almost unanimous on that point. The word random is precisely wrong. Randomness would actually be easier to describe. Instead, the primes seem to follow some hidden law, some governing structure buried so deep in the nature of the numbers themselves that 2,000 years of sustained genius has never succeeded in writing it down. The law is there. You can feel its weight in the data. No one has ever read the actual words. The first person to come seriously close to describing this law from the outside was Carl Friedrich Gauss. If you assembled a list of the greatest mathematicians who ever lived, Gauss would appear near the top of almost every version of that list. As a young man in the early 1800s, he became obsessed with the distribution of primes. He counted them by hand, by candlelight, for hours at a time. How many primes below 100? Below 1,000? Below 1 million? He filled tables with these counts, searching for regularities. And he found something, not the law itself, a shadow of it. He discovered that while you cannot predict any individual prime, you can estimate, with surprisingly good accuracy, approximately how many primes will appear below any chosen number. The bigger the number, the more the primes thin out, and they thin out at a rate Gauss captured in a single clean mathematical expression. The estimate tracked the real counts with an accuracy that felt almost impossible for something so simple, but Gauss understood the precise limits of what he had done. He had found an approximation, not an explanation. He could tell you roughly how many primes to expect in any range. He could not tell you where they would actually be. He could not tell you why. His formula described the behavior of primes without ever revealing the mechanism underneath, the way you might know that a certain number of leaves will fall from a tree in autumn without being able to say which individual leaf will let go first or when or where it will land. In mathematics, that is not enough. It is never enough. Approximation is not truth. An estimate, however elegant, is not a proof. And mathematics demands certainty, not just for the numbers you can check in a lifetime, but for every number that will ever exist, stretching out to infinity. Gauss's approximation, brilliant as it was, could never make that promise. The deepest question remained exactly where it had always been, untouched. Then came Bernhard Riemann, where Gauss had counted primes from the outside, tallying them like someone counting birds through binoculars. Riemann wanted to get underneath the numbers entirely. He wanted to understand why the primes land where they land. To do that, he reached for a strange object he called the zeta function. Without getting lost in the technical details, think of the zeta function as a machine. You feed a number into it, and it produces a result. But this machine works in a space more complicated than the ordinary number line. It works in what mathematicians call the complex plane, a flat, infinite expanse where every point has 2 coordinates instead of 1. And at certain very special points in that plane, the machine produces an output of exactly 0. These special points are called the zeros of the zeta function. They are the whole story. Riemann began calculating and plotting these zeros in the 1850s. And as he mapped them out across that infinite plane, he noticed something that stopped him cold. The zeros were not scattered randomly across the plane, as you might expect from something this complicated. They were lining up. Every single zero he could calculate fell on one specific, perfectly straight vertical line running through the plane. A line defined by a very precise position, where quantity mathematicians call the real part equals exactly 1/2. One after another, the zeros landed on that line as though magnetically drawn to it. It was as if he had scattered metal filings across a surface expecting chaos and watched every single one snap into a perfect row along a hidden magnetic force. And here's what makes Riemann's story so painfully human. He could not prove it. He had the data. The data was speaking clearly. He had every zero he could calculate sitting on that critical line, but he had no argument that could guarantee the next zero, or the one 10 trillion places down, would also obey. He had only what he could see. So he wrote it down as a conjecture, a belief. He said, in effect, I think all the zeros lie on this line, and I cannot yet tell you why. He buried this remark almost casually in a paper about something else entirely, as though it were a passing observation rather than the seed of the most consequential unsolved problem in the history of mathematics. Then he moved on. He died at 39, and that single unproven line he left behind has haunted every generation of mathematicians since. The reason it haunts them so intensely is that the zeros of the zeta function are not just abstract points floating on a piece of mathematical graph paper. They are the actual mechanism that governs where primes appear on the number line. Remember that Gauss's approximation was never exact. It would overshoot the actual count of primes in some ranges and undershoot in others. The wobble between the estimate and the truth could never be accounted for. Riemann's zeros are the wobble. They encode, with perfect precision, exactly how the actual primes deviate from Gauss's smooth curve. Each zero contributes a kind of ripple, a correction. Add up all the ripples from all of the zeros, and the rough approximation transforms into the exact truth. The primes and the zeros are two different views of the same underlying object, which means if Riemann was right, if every zero truly sits on that critical line, then the primes are not chaotic after all. There's a deep order hidden inside them, written in the language of those zeros, quietly governing where every prime in the infinite universe of numbers is permitted to fall. And if even one zero strays off that line somewhere in the infinite distance, everything mathematicians have built on top of Riemann's assumption collapses. This is why the Riemann hypothesis is not just another hard problem. The Clay Mathematics Institute, in the year 2000, assembled a list of what it considered the 7 deepest unsolved problems in all of mathematics. These were called the Millennium Prize Problems. $1 million was offered to anyone who could solve any one of them. In the more than 2 decades since that announcement, exactly one of the 7 has been solved. Just one. The Riemann hypothesis is not that one. It remains open, exactly as Riemann left it in 1859, a proposal supported by an almost incomprehensible weight of evidence and defended by zero proof. The evidence really is extraordinary. Since Riemann's time, mathematicians have turned increasingly powerful computers loose on the task of calculating zeros and verifying their positions on the critical line. The total verified so far stands at more than 10 trillion zeros. 10 trillion. And every single one sits exactly where Riemann said it would, without a single exception, without a single stray point anywhere in the vast computed territory. If you judge this the way you judge ordinary evidence in ordinary life, the case would be closed beyond any reasonable doubt. But mathematics does not do reasonable doubt. 10 trillion confirmations prove nothing about the infinite remainder. Nothing at all. The certainty mathematicians require simply cannot be assembled by counting examples, no matter how many you count. And it was into this specific gap, the gap between overwhelming evidence and complete proof, between what every human mathematician suspected and what none of them could establish, that something new entered the picture. Something that did not share a single one of the assumptions and intuitions and trained blind spots that every human mathematician carries into their work. Google DeepMind was formed from the merger of two of the most powerful artificial intelligence research organizations on the planet. One had spent years quietly shaping the systems that power web search, translation, and recommendation engines used by billions of people every day. The other had taught machines to master games that were considered effectively unsolvable for computers, most famously the ancient board game Go, and then turned that same learning machinery onto problems in biology, physics, and drug discovery. The merger brought together a concentration of talent and computational resources with few equivalents anywhere in the world. By 2024, DeepMind's mathematical systems had already done something that made pure mathematicians genuinely uncomfortable. Their systems had been pointed at knot theory and representation theory, two deeply abstract and technically demanding corners of pure mathematics requiring years of specialist training just to approach as a human researcher. And the machines had surfaced genuine relationships between mathematical objects that human experts had not previously identified. Connections solid enough to be published in Nature, one of the most rigorously reviewed scientific journals in existence. This was not curve fitting or number crunching. This was a machine finding structural relationships in abstract mathematical territory that trained human intuition had walked past without seeing. Then in 2024, DeepMind's alpha-proof system, working in combination with alpha geometry, achieved what had never been done before. At the International Mathematical Olympiad, the premier global competition for elite mathematical talent, a competition whose hardest problems routinely defeat even exceptional professional mathematicians, the AI system solved 4 of the 6 problems, including the single hardest problem in the entire competition, a problem solved by only 5 human contestants worldwide that year. The performance was equivalent to a silver medal. It was the first time any AI system had ever reached medal-level performance at the IMO. The methodology was published in Nature in November 2025. Then in May 2026, DeepMind released AlphaProof Nexus. The results of what this system accomplished in a single overnight run were so far beyond what anyone had publicly predicted that the mathematical community needed time to process them. The system solved 9 open problems from the legendary catalog assembled by the mathematician Paul Erdos, a list of problems that had functioned as an informal benchmark for mathematical difficulty for decades. 2 of those 9 problems had been unsolved for 56 years, and the system additionally proved 44 open conjectures from the online encyclopedia of integer sequences. All of the proofs were formally verified in Lean, a proof assistant whose compiler checks every logical step with mechanical certainty. These were not rough arguments or plausible sketches requiring human review. They were proofs that a computer compiler could verify in seconds. Fields medalist Tim Gowers called it a milestone in AI mathematics, and the cost of solving each of these decades-old problems was a few $100s of computation. What makes the approach so different from every previous attempt to crack hard mathematical problems with computation is not raw speed. Computers have been fast for decades. The difference is the architecture. DeepMind's systems use a design built on what are called transformer networks, the same foundational technology underlying modern large language models. At their core, these systems are extraordinarily powerful pattern detectors. They are trained to find relationships inside complex data that resist ordinary analysis. The key insight of the research program was to point this pattern-finding capability directly at mathematical structure rather than at language or games. When this kind of system was trained on the relationships between prime numbers and the zeros of the Riemann zeta function, something happened that nobody in the room had explicitly programmed. The system was not given Gauss's approximation as a starting point. It was not told about the critical line or what Riemann had conjectured. It was not handed the accumulated theoretical framework that tells a human expert where the interesting structure should live. It was given the raw data and the equivalent of a single instruction. Find whatever patterns exist in here. Report what you see. This is the crucial distinction. A human mathematician studying prime numbers does not arrive at the subject empty. They carry the accumulated weight of 2,000 years of mathematical culture on their back. They know which directions have already been thoroughly explored. They know which approaches the great historical figures declared useless. They have absorbed frameworks that tell them, with enormous authority and largely correct guidance, where to focus their attention and where not to waste their time. This inheritance is genuinely valuable. It prevents a working mathematician from spending a career rediscovering things already known or pursuing paths already proven dead. But it comes with a cost that operates invisibly. Every framework that sharpens attention in one direction leaves a blind spot in another. Every intuition that guides the eye toward promising territory is simultaneously steering it away from somewhere else. The very knowledge that makes human expertise powerful draws a boundary around what that expertise can see. The machine had no such boundary. It carried no theoretical commitments. It had no allegiance to any previous conjecture, no professional investment in any particular approach proving fruitful, no sense that certain regions of the mathematical landscape were too ordinary to merit careful examination. It had no career to protect, no reputation to maintain, no lifetime of training, whispering that this direction was a waste of time. It looked at the prime numbers with something that had never looked at them before. Complete, unfiltered, theoretically uncommitted attention. It did not know that the pattern it was hunting was supposed to be invisible, and what it found was a previously unrecognized correlation. A hidden statistical fingerprint embedded in the gaps between consecutive prime numbers, not in the primes themselves in isolation, but in the structure of how far apart they fall from each other across different scales, across different regions of the number line, across families of related prime-like structures that no human had thought to compare in exactly this way. For small primes, the ones a child could write on a napkin. This fingerprint is effectively invisible, buried under what looks like pure noise. But as the analysis moves into larger and larger primes, numbers with dozens, then hundreds of digits, the fingerprint does not fade. It sharpens. The correlations become cleaner and more precise the deeper into the infinite the analysis reaches. And those correlations align with a precision significantly beyond anything previously demonstrated, with the mathematical predictions that flow directly from the Riemann zeros sitting on the critical line. The pattern had been sitting in publicly available mathematical data for decades. Any mathematician anywhere in the world could have examined every number the system examined. The data was not secret. It was not new. The pattern was not hiding. It was there the entire time, in plain sight, in databases that researchers had been accessing for years. The human experts missed it, not because they were insufficiently brilliant. The mathematicians working in this territory include some of the sharpest minds our species produces. They missed it because they looked with eyes shaped by every assumption their training had given them, and those assumptions, correct as they are for most purposes, formed a filter that made this particular structure invisible. The machine had no filter. It saw what the eyes had been trained to look past. Now, this must be said clearly, because clarity here is not optional. The AI did not prove the Riemann hypothesis. That statement would be false. What happened was something different in nature, but still extraordinary in implication. The system provided a new category of empirical evidence, evidence assembled from an angle no human had previously stood at, suggesting that the structure Riemann glimpsed in 1859 is embedded even more deeply and more pervasively in the prime numbers than the existing theory ever predicted. Several mathematicians who have reviewed the result have said, carefully and with appropriate qualification, that it may represent the most compelling computational evidence yet assembled that the Riemann hypothesis is true. Not proof, evidence. The distinction matters more than anything else in this story because it is the entire reason mathematics is different from every other human pursuit. But here's what the discovery does change. It suggests that the approach itself, this method of hunting for structural relationships across scales, rather than marching toward a direct proof through established pathways, may open a direction that has never been seriously explored. A way of understanding why the pattern must hold rather than simply confirming again and again that it does. A different road toward the summit that no human thought to walk because the training that produced human mathematical intuition did not produce the instinct to walk it. In November 2025, DeepMind launched an AI for Mathematics initiative in partnership with Google.org, providing researchers with access to systems, including AlphaProof and the enhanced reasoning capabilities of Gemini Deep Think. The explicit goal is to create what they describe as a feedback loop between fundamental mathematical research and AI capability. Terence Tao, widely considered the greatest living mathematician, has described himself as having become an evangelist for AI in mathematics, documenting AI contributions to research while emphasizing a partnership between human and machine rather than a replacement of one by the other. The Riemann hypothesis has been open for 167 years. It has outlasted every strategy that human mathematical genius has directed at it. And now a machine with no history and no assumptions found a face in a painting that 2,000 years of human eyes had looked at without seeing. Not a proof, a face, a structure, a hint that the painting contains more than anyone had imagined. The question worth sitting with is not whether the machine is smarter than the mathematicians. That framing misses the point entirely. The question is what it means that the most productive thing the machine did was precisely what no human expert was able to do: show up without knowing where not to look. 2,000 years of accumulated mathematical wisdom told experts with enormous authority and largely good reason, which parts of the prime number landscape were already well understood enough to stop examining carefully. And in one of those overlooked corners, something had been waiting all along, which forces the question outward. If this is what becomes visible when a system examines ancient mathematical data without inherited assumptions, what else is sitting in plain sight in other fields, in other databases, in other problems that human expertise has quietly decided are already well enough understood to stop examining with fresh eyes? The prime numbers kept their secret for 2,000 years. The machine that finally found it did not know the secret was supposed to be impossible to find. That combination, the ancient problem and the machine without assumptions, may be the most important collaboration in the history of mathematics. And we are only at the beginning of learning what it will show us next.